Um, okay, so yeah, before I ended the last part of the lecture saying that I want to move the dark content part to this lecture now. So, there we go. But actually, since I had a couple of questions in this direction, I actually want to go back to this slide because a few of you asked me a little bit on clarification of this process, and just to connect back to what I discussed there. So Dharmic M, Sensei, Supersymmeters, H3 EV, what they are observing are individual electrons. So they are quantized, they are just, you can count them, it's 1, 2, 3, 4. It's really, this is what is being measured. From the theory side, this is what is being predicted for dark matter scattering in a silicon target. But in general, really, it could be any spectrum that you have here. It could also be your background model, so it could be either your silicon 32 spectrum or some tritium background or whatever. So you could have any kind of continuous energy distribution here that is being predicted. And now the question is, how do you connect those two? So when you have a measurement, you want to compare your measurement with a prediction. But in this case, we first have to get from the continuous part to the quantized. And so from this direction to here, you can't really, you can do it with unfolding techniques, but this is the harder part. To first order, I would say when you have like one electron hole pair, you don't know exactly what energy it had. It could have a range of energies generating one electron hole pair. But you can go the other way around and say, given a certain energy, what is the probability to get 1 or 2 or 3 electron pairs? So in the end, it's really a probability distribution that you fold over, and the probability depends on where in this space you are. So coming back to also this is a slide that I used in the last lecture, and so for example, having a transition that does not require any shift here in momentum, this is more likely to happen than something where you need less energy, but still, so since we are close to zero temperature, you get less support from the phonons to actually make the step also in terms of the momentum. So it really what it comes as part also not only for the dark matter prediction in general, but also for how much energy you need. Actually, this is where I want to get with this slide. Two things as a reminder. You have here for silicon the direct, the band gap. So this is an indirect band gap. So the band gap is the lowest difference, the smallest difference between the highest valence band energy level and the lowest conduction band level. So the band gap is around 1 eV. Now, the average energy that you need in order to create an electron hole pair is higher than that, and that's for multiple reasons. So one reason being that you also lose energy when you just you have the energy, but then you lose energy also to your material, and then also the other part is that the one energy. The 1 eV is only enough when you have support in moment part. And this is when you bring this now together, the ionization model, and this is the model that I'm showing here. Here is really just first order. Again, we have the gap energy. So for silicon, about 1.1 eV. The average energy epsilon that you need to create an electron hole pair is 3.8 eV. So this is to say, if you have an incoming photon that has about a bit above 1.1 eV, it could give you a photon, an electron. So let's start one step earlier. If your photon, your incoming photon in this or incoming particle in general has less energy than a gap, then you just don't get an electron. So if your incoming particle does not have enough energy to get the electron from here to here, you get none. If your incoming particle has more energy than the gap, but less than the average energy that you need to create an electron pair, then you get 1. And then if you go above that average energy that you need, then you divide the energy by the average energy that you need in order to get an electron hole pair. Now, I said it multiple times, the average, this is the average energy, and you can also see that this is the average number of electron hole pairs that you get. So say you have 10 eV energy of your incoming particle. These 10 eV on average, or let's use 12. You have 12 eV on average. They would give you 3 electron hole pairs on average. But we don't want to just have the average. We want to say, given a certain deposited energy, what is the probability to get those 3? Sometimes you will get 2, sometimes you will get 4. So the question is, what is the probability to get exactly 1, exactly 2, exactly 3? And so this, in the end, this whole process, this whole transformation from here to here is really, again, just applying a probability, a PDF probability distribution from given a certain energy, what is the probability to get this and that many electron hole pairs. And this is what you have to do when you, again, when you want to actually use your data that is quantized and compare it with the model. And again, I'm saying here first order, because what is hidden behind here is actually rather complex. So we have here, coming to you in a moment. In this model that Superstream S was using, there is a binomial distribution behind it, taking the Fano statistics into account. So it's really that part here is much more complex than what is shown here, and it's still just a model, and it really depends on how well you can measure your Fano statistics that your prediction is getting better and better. You had a question. Yeah, because that's just the average energy that you need. But in principle, it is enough if your energy is larger than the gap energy. So in principle, it's really, you can already get an electron if you have enough energy to get it from here to that level here. So if you can cross the indirect band gap here, you just need that 1.1 eV. So if you have a particle that has more than that energy, but less than the average, that's good enough to give you one. Good. So that just again because multiple people asked, and so I figured let's discuss this a little bit in more detail. But now coming back to what I wanted to actually start with this round is dark Compton scattering. So I ended my last presentation saying then if you go to higher incoming dark boson energies, the photoelectric cross-section actually drops significantly, and Compton scatterings, just in standard model physics, Compton scattering gets a higher cross-section. And the question was, okay, if that's the case, so in this whole dark absorption process, the connection to the photoelectric cross-section, actually that's also something that I should have said earlier, so the time with the photoelectric cross-section is just a kludge, a simplification that is helping, or that's simplifying the modeling. And the same idea, if you go down and really in detail and do the calculation, you don't just plug in the photoelectric cross-section, but still it's super closely related to the principal idea. And the same could actually apply to the dark Compton scattering, and that's also something that's not new. So it's not like, new, but typically you have it the other way around. But here the thinking is you have an incoming dark boson, so the dark photon or the axion-like particle, and it would scatter off an electron. And then in this case, you have here at the vertex, in the end, you convert the incoming dark boson into a standard model photon. And one thing that is important that I also mentioned before, the dark Compton should have quotes because Compton scattering is on free electrons. We are here in a bound system, but if you have at least enough energy to release the electron from its bound state, then a free electron approximation is okay. but still ideally you should go and take atomic effects into account. But this is also to say when you're not having enough energy to free the electron, then you shouldn't use free electron approximation. But let's stay in this regime, because in the end, I also mentioned that dark Compton only becomes interesting at a couple of 200 keV dose for germanium. So that's fine. So the binding energies are EV scale. So we are actually nicely in that regime where at least the electron is being freed. And now you have two Feynman diagrams, but in either case, what you have is again the incoming dark boson and the outscattering photon. And what you want to measure is the electron again, and the electron has the incoming energy minus the outgoing energy of the boson. And in this case, again, you want to know how the rate scales with the coupling. So this is either the kinetic mixing or the coupling to the electron. So again, dark photon or the axion-like particles. And the other scaling term is the electron density over the target density. So this is always a material-dependent part where you need to think, okay, what is a good material for this kind of cross-section or for this kind of absorption? And you see in the end, the scaling, this was for the dark absorption, it's the same. It's the quadratic scaling, so it's, we didn't get away with that part, so we still have the coupling squared. But this is just here what I said also. Here we can model it such that we plug in the photoelectric cross-section here. And again, this is where then in the photoelectric cross-section you have the material dependence inherently. And here again, it's the electron density over the target density. Let me. It depends on where you are in the energy scale. So when you are at above, I think it will come. I will show you slides in a moment where you see that the Compton scattering is stronger than the absorption if you are above 100. No, it's heavy. It's not faster. It's heavier. You will see it in a moment. There's a slide. So it was part of the first lecture this morning, but I will. There will be a plot that will help with that. So actually, here it is. Here, what is shown here? So let's just focus. Yeah, it's the two plots. One is for the coupling. See? It's mass. We're having cold dark matter. So this is really the mass scale. And so what you're seeing here, so the dark, these here, those with the zigzag, these are from absorption, right? And photoelectric absorption, if you just stay in the standard model picture, when you go to higher photon energies, or here dark boson masses, it really drops, right? It drops to 1 over energy cubed, the photoelectric effect. And so since this rate scales with it, as the photoelectric cross-section drops, the rate drops, and the other way around, the sensitivity gets worse and worse. Whereas Compton scattering, when you go to higher energies, or in case of dark bosons, higher masses, this is where the Compton scattering, at some point it starts to take over, and you would want to focus on, for example, the electron density in carbons and diamond detectors is very high, and you see that actually here at around, so this is what is this, 30-ish kV or 40. This is where actually the Compton scattering, the sensitivity to this to this coupling comes from Compton scattering. So the photoelectric or the dark absorption would go up like this. And so you see here it's now at 100 kV. This is over an order of magnitude boosted by the dark Compton. So if you're at higher masses, Compton dominates. The dashed, so the solid line is basically telling you which is the total cross section. If you take both of them together, so the dashed is just dark absorption, and the light solid is dark Compton, And when you have, if you combine the cross sections, you have the dark solid line. Yeah. Yes. It's a constraint on the. Yes. 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 And so then, just also coming back for germanium, this is where I stopped the last lecture. For germanium here, and so the thing is right now we don't have diamond detectors that are helpful here, but we do have germanium detectors, for example. And here you have germanium as the orange one, so the sensitivity using the dark absorption goes this way, and the one from the Compton goes this way. So it's an order of magnitude improvement at the highest difference. Now, the thing with the Compton scattering is you have to keep in mind that what scatters once, the outgoing photon is now not a dark matter, a dark boson anymore. It's a standard model photon, and so every time before, I'm always saying, okay, dark matter, it scatters once and then not anymore. But in this case, you have an incoming dark boson, but what is going out is a photon and the electron. The electron will remain in your detector, but the question is, will the photon scatter again? If it doesn't, if you have like a thin detector, you can calculate the probability, Lambert law, whether this will scatter again or not. If you have a thin detector, then basically you're really just measuring the energy of the electron, and this again is the incoming minus the outgoing boson energy. So this would be at a lower energy than the absorption, because a lot of energy is still carried away. So this is again the dark absorption peak I discussed before. So you have the deposited energy is the mass of the dark boson, and here you have a little bit more of a more complicated expression than this, but in the end, it's just saying that the electron gets just a fraction of the incoming energy. Yes?
I'm pretty sure I know the answer, but people haven't done the same for phonons, right? Where you basically absorb and then you create another phonon, right?
Yes.
Right. Instead of emitting a photon, you can also emit phonons if you're talking to the nucleon.
Yes, I don't know whether I've. Yeah. Yeah, I don't know who. Yeah, but I mean, these are all the tricks that we are playing, right? So we are trying to see how we get from a coupling what couples what with what probability. So yeah, yeah.
It's not for these energies. It would be so much lower. And
Yeah.
Scatter off a phonon.
Exactly. So I think uh, Tonyang, Yonid, and so on. I think they have looked into this at some point, but I'm not sure. But if anyone, I would think them. Um, Okay, so but the thing is that typically, so for this you need to have a small detector so that the photon actually goes out without further scattering. So what you often, or what the other extreme would be, maybe you have a super thick detector, and then so you have the initial scattering, but then the photon scatters. In the end, all of the energy is being deposited in your detector, and if that's the case, then actually, if the total energy is deposited, then the Compton the Compton energy to be observed is the same as the absorption energy to be observed. So it's really again here you have a fraction of energy is leaving with the photon. Here all of the energy is being deposited, and the energy is the mass energy coming from the incoming dark boson. And if all energy is being deposited, it's the entire mass energy, and that's the same case as for the dark absorption. So in this case, your two peaks would overlap. In reality, with the current detectors, we are somewhere in the middle. So we have, first scattering, and then we have a couple of scatters, and then the photon leaves. So you have a fractional, of a fraction of the total energy, of the total mass energy that's coming in here. And so this is the moment where you actually need proper simulations of your detector in order to see how much of the energy, depending on where the dark boson is starting to scatter. So if it scatters like outside, then probably the photon is going to leave without scattering. If it interacts for the first time here, then it will probably scatter a lot. So you really have to do a proper simulation to get the distribution. And the other thing is also that, let me just quickly go back. This is the one extreme that I said. So if there's just a single scatter, you have the peak of the Compton here. If everything is deposited in your detector, then the peak would be here. And if it's somewhere in the middle, then this really means that this peak is walking over to the other peak. So that's a little bit more of a challenge for the Compton signature, but in the end, you can simulate and you can calculate it. And the nice thing is there are two things to consider. So say we are always talking about lower threshold for detectors. That's not the only thing. Often we also have an upper threshold, an upper energy threshold, where basically our detectors are non-linear anymore. So you're getting into saturation, and often you can also imagine that some detectors are absolutely not able to measure 200 kV because it's saturating the device. The threshold would be here. You would be missing these dark bosons if you were just relying on absorption. However, if you have a dark Compton peak, you actually can still see it because it's below your high energy cutoff. Or the other thing is, if that's not the case, you actually have a scenario where you're still sensitive to this. Actually, the other extreme is nice. So actually, it's nice also that you have now two correlated peaks, because I said before it's really annoying to search in a peaky background, a peak structure. If you now have a two-peak signature with a very well-defined ratio, amplitude ratio, that is already helping with your identification. Or if you are in the situation that you actually have a thick detector and this is just on top of it, you also have a higher peak, so you have more sensitivity. So one way or another, taking the dark Compton into account in that region where it actually starts to dominate can improve your sensitivity. Um,
So the number of events in absorption for this single simulated model is larger than the comp, because the Compton rate naively is suppressed.
No, but we are again at that regime where the Compton scattering is more probable than the absorption.
That's because
Yeah.
you don't have an energy gap that is large enough to absorb it? Or?
No, it's so basically when you are maybe let me just quickly go back to my.
I mean, he's right, right? This occurs basically when there's no more shells that every once in a while like jump up, right? This is when you reach the asymptotic formula.
Exactly. So it means that you don't have a bound, you can't absorb it. Because,
I mean,
You can still,
you can.
the probability is lower.
Yeah, but, well, you can absorb by which is one.
No, you could just ionize.
No,
Yeah.
So you ionize, but it's much more worth it if you also emit it.
but even photoelectric effect is not zero.
Yeah. Yeah.
Okay.
101.
Yeah, so this the material dependence is here. So basically, when you just want to pick one material, so for example, xenon, you would see that at about zero 0.4 MeV incoming photon energy, the Compton effect starts to dominate over the photoelectric effect. For germanium, it's happening a little bit earlier, and this is really also going back. To this picture, this is how the photoelectric absorption scales, right? So this is here is this is germanium. You have the indirect band gap here. Then you have around here the direct band gap. So this is where really the photoelectric cross section is highest. And then depending on the shell where you're getting, it really drops further and further. And this is
Photoelectric for you is defined with a non-shell photon.
So the photoelectric is really right now, just really standard model. No. Yeah. So well,
because at some point I will have enough energy to
yes, but
plus minus.
Yeah, so this is when you are pair production. So this is really in this, yeah,
There's a gap. I said, okay,
yeah.
thanks. I understand. Sorry,
No worries.
I missed the lecture.
Yeah, and yeah, just quickly something that I mentioned in this lecture as well. When you have a dark photon, for example, that has enough energy to create an electron, E plus E minus, it's not a good relic dark matter candidate anymore because it would do this all the time until it's just gone. So you want to have, if you want to have a dark boson as a relic dark matter particle, it should not be heavy enough to create E plus E minus because it would decay away. So that's also something. Basically, we are stopping at twice the electron mass with this picture. No, so let's get. Yeah, it just. um, So then, basically, what I'm saying is that if you take dark Compton into account, so the existing limits at the time, supersede mass, Edelweiss, Gerda. So these, for xenon, I mentioned already, it was actually good that we went back to that plot. For xenon, the transition where Compton scattering gets stronger than photoelectric cross section is at higher energies. Whereas for germanium, it's at about 200-ish kV. So this is about here. So this is where dark Compton. If you include this in your limit calculations, then you see that you actually have really an increase in sensitivity of your data. And so that's basically one thing why I wanted to discuss this, because this is one of these examples where really theory meets experiment, because this data at that point had been published already, and basically it was Jonit and Eric, theorists, myself and Tochin, experimentalists, we were just getting together and saying, okay, look, this, if dark absorption is there should be dark Compton. What does it do to our limit? We were not, so we were using existing data and just recasting the limits. And that's always fun, that I recommend to both sides, either if you're experimentalist or theorist, get together with the other side, discuss what you could do, and see what it does to your sensitivity, because these are the things where this is basically for free, so you don't need to build a new experiment, you just need the people getting together, and yeah, you do it on an experiment. We do a lot in order to improve our sensitivity by a factor of 2, 3, or in order of magnitude. We put a lot of money in there. So sometimes it's also helpful if we just see what we can actually get out of the data. So this is just an example, yeah.
This was from our Verda paper, or what?
Yes.
I wasn't sure whether you realize, because Master and Yannick, you also, I mean, you use them
Yeah.
to reanalyze, as you say, right, the Verda data.
Yeah.
And then we do this effect.
Yeah. So no, we really just took the original limit. Yeah. Yeah. The plot where it is. Yeah. I can send you the link later. Yeah. So yeah, so that's just something again to point out that it's really theory and experiment should work together to get the most out of our knowledge. So now coming to the actual third part finally. So we now talked a lot about phonon detection. I told you how you can take photos of your particle interaction with the CCD cameras. And now I want to go to the third part, the light target detectors, because in the end, and yeah, this time I'm always telling you which interactions I'm looking at. Coming back to this picture, this time we are back actually to dark matter nucleus scattering, this spin independent one, because we are now at that point, so we discussed lowering the threshold in order to get to lighter masses. I now, in the second lecture, I discussed how you can also exploit other interaction channels. And actually, sorry, I want to, now that I transition between, sorry, I need to, between the different, okay, anyway, I don't know. So this is what I want to do this time. So the third way how you can face the low mass challenge is if you are increasing the recoil energy. So what we have discussed, Marco discussed liquid noble gases. I discussed yesterday cryogenic calorimeters for charge readout. Paolo discussed the scintillating crystals. So those are all technologies you have learned about already. This lecture, we will come to something that lies on this part of the triangle, to measuring phonons and light, but in this case with a superfluid. And in this case, superfluid, more precisely, is superfluid helium-4. Depending on the time, I will also want to go to proportional counters using gas inside. And if time permits, actually also liquid noble gases, there's one proposal out there using helium in the TPC, and in this case it's not as a superfluid but as a normal fluid. So let's see how far I get, whether we get to this point, but the cooler parts are actually these two anyway. And so let's start with this part. So increasing the recoil energy is actually super easy when you yeah. So now I'm just missing my preview since I skipped between the slides. But okay, anyway. So let me before motivating why using superfluid helium, I want to mention which two experiments are planning to use it or are using it in their prototypes. So Herald is the one experiment in the US, and Delight is a German-based experiment, and both are having the goal to use superfluid helium-4 in a cell. And the Pro, again, this is a phonon, this is a calorimeter in the end, the same as with the heat wave detectors with the SuperStream S H3EV and Edelweiss and SuperStream S, is that you get 100% of the deposited energy if you're measuring the heat signal. Low energy threshold, I mean, that's also the goal here, not only that you want to increase the recoil energy, but still it's nice to also have a low energy threshold. The disadvantage in this case is a rather slow signal. So it's a millisecond scale. This can be challenging if you want to increase your detector. Now, Herald and Delight both are in the prototype phase. So here you see, this is, again, just a prototype. There's about 10 gram of superfluid helium in here, and you see here how a pulse looks like. You will learn over the course of the next slides why it looks the way it looks. And this is for Delight, the prototype. This has about 150 the full scale will have about 150 gram helium-4. That is about twice less than we actually have in the prototype. So the prototype is of the size of a coffee mug, really. So this is about 300 milliliters. So if you, again, just a expensive coffee mug. And what the prediction is for helium, so this is taken from the community report. Here's it again, GV, this is 1 GV, and here you see all these experiments crunched up here. And I will comment on these lines because some of them you can ignore for now. They are experimentally not achievable, but this is basically telling you what the helium itself is giving you in terms of reach. So again, experiment is failing to get anywhere near in the foreseeable future, but just the helium itself would be able to go all the way down to the sub MeV scale. Now, why helium? I mean, it is clear. I told you we want to increase the recoil energy, and when you just consider, instead of having this fat thick nucleus, for example, from xenon, which is a super heavy guy, and instead shrink your nucleus to something rather small, then the kinetic, the energy transfer is just much more efficient. I think that's easy to take. And then just in terms of a plot, so this is the differential rate. And clearly what you're giving up is this A squared boost. So I'm back in the spin-independent nuclear scattering, and I discussed yesterday how the scattering rate, the cross-section for it, scales with the size of the nucleus to the squared. So this is why actually xenon is really, really great. if the dark matter is heavy enough. So here you can see actually in black how the Zener rate really rockets. You have many more orders of magnitude in rate compared to a small nucleus. However, if this is here your energy threshold, it can be infinitely large. If you can't see it, it doesn't matter. So that's basically the approach for the light elements, giving up on the A squared enhancement. I mean, it's still A squared enhanced, it's just not that strong, but you get a larger recoil energy that you are actually able to observe, even if your threshold would otherwise for the other materials not. So this is the key idea: enhance the recoil energy. And so the goal or the general picture for both Herald and Delight is, again, you have basically here you have the superfluid inside, so you need to cool it down to millikelvin temperature. And actually, so to be in a superfluid phase, you actually just need to cool down to below something like 2 Kelvin. But you want to go to the millikelvin phase because what you have in superfluid helium is also phonons and protons. And so basically, in a crystal, I described it as you can consider it as lattice vibrations. Here you can picture it a little bit like sound waves. You don't have a share, which you would have in a crystal, but still you can picture phonons and protons here as a sound wave. And this will be super relevant for the whole idea of using superfluid helium. Then and yeah, so in order so when you are just below the threshold for the superfluid phase, you still have a lot of phonons making up your thermal background. So it's the same idea like with the crystal. So I mentioned that you want to really cool down your crystal to a state that all the atoms are more or less sitting still in their position, so that you're sensitive to the tiniest movement, so the tiniest phonon wave. That's the same thing here. So if you have a lot of thermal phonons fluctuating around, the signal might be hidden in it. So you really want to go down to very low temperatures so that you really barely have any scattering sites for the phonons, and really have no phonon background, and just the phonons that are induced from the original interaction. And then you have something called excimer. I will come to that in a moment. And then you have photons coming out. So in the end, this is similar to the whole crest idea, where you have phonons and light that you want to collect in the end. And so for this to happen, you need to have ultra-sensitive sensors that are picking up that energy. And so that's the very big picture. We go down this whole detection scheme in great detail now. Just a short comment in terms of phonons and protons. So this is the dispersion relation, and basically just protons are really just high energy, high momentum phonons. So whenever you hear protons, so some people even ask the question, why did we give them a different name in the first place? But for you, just you have here this linear regime, and then you have the high momentum regime, and this is where we refer to as phonons. But this is just a side comment, because you will see it every so often, phonon/proton, so this is it. And then, in order to not always having to say it, we also just sometimes refer to it collectively as quasi-particles. Now, what is happening if you have light dark matter scattering off your helium nucleus? And these couple of slides should remind you a lot on what Marco also presented, because in xenon it looks very much the same. So this is both a noble gas. The one difference is the whole phonon part, but here at the beginning we are not starting with the phonons, we are starting really just with excitation. When you have an excited helium atom, it doesn't want to stay alone, it directly binds to a molecule with another helium atom and forms an excited dimer, so a molecule of 2 helium atoms that is excited, which is called excimer. And then it depends on whether your excimer is in a singlet state or in a triplet state. The ground state is a singlet state. So the singlet to singlet transition goes immediately, basically, order of nanosecond. And the transition energy that you're getting gives you photons in the UV range. Then, if you are in a triplet state, if your excimer is excited in a triplet state, then the transition to the ground state, of course, takes ages. And on particle scale, so this is really a 13 seconds, it's forever. Now, I should give a little warning because this always confuses people a little bit. It's true unless the excimer comes in contact with a surface. If the triplet excimer reaches a surface, then basically the transition is induced by the interaction with the surface, and you directly get a decay into the ground state in that moment. So if you have no surface, the triplet would just walk along until it decays. But instead, in reality, you have a detector, and so the triplet would reach your sensor or something and then decay into a UV photon, and again, you get a UV photon. And this is more on the millisecond scale, depending on your geometry, of course. When you're closer, it's faster. If your walls are further away, it takes longer. Yes, yeah, exactly, yeah.
Do you want it to be short or long? Like, do you strongly care if you're measuring an interaction that happened 10 seconds ago?
Yeah, so you want actually this to be rather closer to the original signal, because otherwise we have these floating events around that every so often you would have a UV deposition that you cannot connect to any event. So you would want it to be closer.
You shove a bunch of like holes inside the sensor and then
So if we scale up, so at this scale we don't need it yet, but if we scale up, we may want to consider something. But also it should be said that they are suppressed compared to the rest of the signal. So it's really, I think, when we come to a scale that it matters, that it's a dominant background, yeah, there are things like a mesh or a grid or something, or rods that are in there, yes. Yes, yeah, yeah. Sorry? Yes. Okay, and so then the other thing that I did not yet mention, so between, when the helium is being excited and forming the excimer, typically it could be there a little bit more excited. So you have the ground state, you have the first excited state, and some shallow states above. And so first you would have these de-excitations on those levels, and then the full de-excitation. So this is typically, so from the higher states to the first excited state, and much closer the energies, and so you would get IR photons. So you also have those, and the same is the same course of signal propagation is actually happening when you have an ionization. So what is happening if you have an ionization happening? You have the electron. There's no electric field applied, neither in herald nor in the light. And the electron will actually recombine with the original helium atom. So this is Gemini recombination. So it's really just it's being kicked out and then it's being collected again. And then you're back in this track. If it's being collected, you are back on the excimer track, and you get your IR photons, UV photons, and triplet excimers that then decay into UV photons. And then you have heat. So this is basically what I said earlier. You can also imagine that the dark matter particle or any particle hits the helium nucleus, and it causes a little bit of a shaking, and so the wave from that propagates away in the form of phonons or rotons. And here comes a trick that will take a few slides of explanation, because the question is, in the superfluid, how do you collect the quasi-particles? And how important are they actually?
So, just to see if I
Mm-hmm.
in order, in terms of threshold,
Mm-hmm.
so the lower threshold is heat, then I have just to check if so then I have excitation, ionization is the other.
Yes, yeah. Yes, and there will also be something that will show this a little bit more, because this is actually exactly the right question you need to ask. At what energy is what part contributing? Because it differs. And then you can say, okay, if there's basically only heat, then you are below the excitation threshold, and you can directly say, okay, this must have had this energy. Or but yeah, this will become clearer. But this is exactly the right point. But yeah, first let me discuss a little bit how you're actually measuring phonons in a superfluid. And this is again this picture here. So this picture is actually a snapshot of this part. So you have in both the Herald and Delight, you have here the superfluid, and then above you have vacuum. And these things here again, these are the sensors. So you have some sensors in the vacuum and you have some sensors in the superfluid. So for the phonons, so the thing is that right now, so theory predicts that the phonons can also be collected, transmit from the superfluid into the wafer. However, it has not yet been observed. And so the thing is really that the phonons come with a certain energy, with a certain wavelength, basically, and whether they couple into the other phonon system, this depends on acoustic match between the two. It's not a God-given that the phonons from the superfluid propagate into the solid state. It's predicted, it's not yet been observed. Now, what has been observed, though, is that when the phonons reach the surface, they kick out helium atoms, and those can be collected. And so this is what I want to walk you through. So let's rotate this whole picture by 90 degrees. So we have now the sensor here, we have the helium here, and I'm just doing this in order to be able to draw a potential. So the helium-4 is bound to itself with a binding energy. Nothing fancy there. It's bound by about 0.6 millieV. That's the binding energy of helium to helium. The phonons that are being generated are of about an energy per phonon of 1 millieV. So they have just enough energy, each phonon, to release a helium atom from its from its own liquid here. And so the helium does this moment here, and now the helium is released and it propagates here to the sensor, so it propagates here. And this is the trick here on the sensor. So if you have helium-4 coming to, for example, silicon or sapphire, the binding energy, so the absorption energy on the sensor is higher than the binding energy here. So it really drops down and falls down into this potential. The absorption and adsorption, not absorption, adsorption. So it's being adsorbed to the wafer, and the binding energy is being released into the wafer. And first of all, the process, this is what we call quantum evaporation, because the phonons really boil off the helium, if you will. So they really evaporate the helium, and then the helium is being condensed on the wafer. And how deep this well is depends on the material. If you have silicon, the binding energy of helium to silicon is about 10 millieV. Sapphire is about 20 millieV, so that's what Delight will be using. So this means for 1 millieV phonon, you get a measurement of 20 millieV. So you get an amplification factor of about 20 without any drift field or anything. And that's actually the nice part, because it's super clean. The moment you have drift fields, there's always, you need to model it properly, because it's not, especially the boundaries, it's not perfectly homogeneous, etc. And you also get noise, and because you have to have the field in the first place. So this is really an amplification factor that's just coming from binding energy. Now, the important part in order to have this is that the sensor here is in vacuum and stays without any helium film. So if you had, for example, here a tiny helium film, you would then not have helium on sapphire anymore, but helium on helium, and there the binding energy is 1 millieV. So you would lose that amplification factor. So we must keep the wafers free of helium. And now you might ask the question, why is there helium in the first place? Because they're sitting in vacuum. And that's what I think Paolo mentioned already yesterday, that I will mention, which is true. I'm going to mention this. Helium-4, superfluid helium-4 is quite annoying in that sense, that it likes to creep up walls against gravity. So on the one hand, it's super cool. Actually, there are experiments that you can do in lectures and so on. It's super fancy to see. If you want to do an experiment with it, it's a little bit annoying. And so basically the thickness of this layer can be calculated. So it depends on the one hand, on the gravitational not constant acceleration, on your density of the liquid helium, Then it depends on how high you are above the liquid, and it depends on the so-called Hamaker constant, which is basically describing the van der Waals forces that are actually behind this effect. And so now this really means it is going up and up and up, and um, that part is in the end, and it also has a certain velocity. It's not like taking forever, but it's really coming up there with 100 centimeters per second. That's not slow. So in an experiment, you cannot just say, okay, we just turn it on, quickly do our measurements and turn it off again. But this is really coming in there. So both Harold and Delight need to avoid that the helium is actually creeping all the way up and then come back from the outside and get on your wafers. And there are two methods that have been proven to work. The one is using unoxidized cesium coating. So cesium and rubidium are the two materials for some reason that will not be wet by helium. Anything else, so the helium creeps up anything else, but cesium for some reason doesn't like. So if you put a cesium coating here, it will avoid it. The challenge with the cesium coating is that it's highly reactive. So first of all, you want to have any oxygen out from the first place, but it's highly reactive, and it really, in the end, it's on the one hand getting dirty, and it's basically you need to renew whenever you operate your detector. You open it up again. You need to first of all first purge out the cesium, because otherwise it would start to contaminate your experiment, and you have to renew it and then recover it newly. So this is something every run you have to renew the cesium coating. Which can be a challenge. The other thing that can be used is a film burn, and this is something that has been used in the past. So this is from the 90s. This has been demonstrated in the 90s by the Heron experiment. So Heron was a neutrino experiment already back in the 80s being proposed for solar neutrino detection. So this is something that you also heard earlier today, that typically these things are not necessarily new. It's just maybe they were at the wrong time, because then solar neutrinos, that experiment was not the right one to solve the solar neutrino experiment. Also from the technology, there were some things that didn't work yet. So sometimes, they were a little bit ahead of their time, but the film burner, that part worked. And so this is an old figure here from the 90s, but you see that basically this looks very much like what I'd drawn before. You have here the helium, you have vacuum, here you have in this case a single silicon wafer, and this is the film burner. And so what the goal is here basically, the helium will creep up the wall, and it will go along here, and here's this opening, because somehow we need to get the sensors in here. So there is an opening, and even if it's just a tiny opening, helium finds its way through. And now it will go here on this system, and now here you have a baffle system with cold baffles and with warm baffles. And so the helium will now start to go around this heated part, and will basically be boiled off. I mean, this is a little bit extreme. You're still in the hundreds of millikelvin scale, but basically you evaporate. That's the better term. You evaporate the helium film, and then here up here you condense it on this plate, and so you basically disconnect it from that part to the other part. So you really burn off the helium film. That is the idea, and that has been built in the past already twice. Actually, two film burners have been built, and they work. So this is something, that Delight will be using, because once it's operational, you don't need to redo the cesium coating, and you just quote unquote need to operate the film burner. Now, so this is now Delight, and you see it's looking very similar. Now the challenge, and that is something that Heron did not manage back then. I just said the film burner is operating between 100 and 300 millikelvin. At the same time, you want to keep the helium at about 10 millikelvin. For a dilution refrigerator that Paolo described yesterday how they work, this is actually not trivial to support these two different temperatures. And then also, I mean, in the end, it's not just the temperature, but really the power that you need to get in order to evaporate the film. So you really, in the end, what Delight will be doing is use a customized dilution refrigerator with one mixing chamber, supporting the temperature here, and the other mixing chamber taking care of this part, so the film burner. And so the problem with uh, Heron was they just had one dilution unit. They were able to operate the film burner, but they were not getting the helium to low enough temperatures. And also the sensor needs to be actually at very low temperatures, and I will explain how these sensors work. But basically, if they are not cold enough, the energy resolution, so they were then in the end at something like 50 millikelvin, which is way too high for their operation. So they managed to operate this, but they were not managing to get this cold enough anymore. And so this is something that will be fixed with 2 dilution units. Now coming to the sensors, because that's the next, yes.
How do you know that the burner will be working? Because the text is you measure something that you know that you don't have a problem with the film of the sensor. What do you measure?
So in the end, I mean, first of all, you notice when the film is starting to actually reach these sensors, you will notice for 2 reasons. So first of all, because your energy response is degrading because you don't have this amplification factor anymore. So if you have a calibration source and without a helium film, you have, I don't know, a certain amplitude, and now if the film comes, the amplitude will go down. So this is also already the moment when you notice. And another thing, if you have an extra layer of helium on here, also the heat capacity of the whole sensor is getting higher and they are getting less sensitive. So this is also very basically a measure, degrading in the observation. Okay, and so in terms of the ultra-sensitive sensors, so Harold will be using or is using TSs. We have discussed them at great length yesterday, so I'm not going to repeat that. Today is the day of the MMCs. And so coming back to this picture, so again, we discussed the TES yesterday. And on this plot now, we are looking into MMCs. And I mentioned when I showed this slide yesterday, so the key idea of any of these temperature sensors is that you use some property of the material that is temperature dependent. And in terms of the magnetic microcalorimeters, the MMCs, you're using magnetization that is dependent on temperature. And so this is basically really just going back to bachelor physics, what you learn during a bachelor degree, Curie law, paramagnetism, the paramagnetic behavior, the magnetization scales as with the temperature like this. And the important part is here in contrast to the transition edge sensor. So yeah, you remember we had here this transition curve, and Paolo nicely explained how the dynamical range of these guys is limited to this region where you are in transition. So above this, you are getting into saturation because any temperature change gives you more or less the same resistance change. You can't really do the trick of a small temperature change gives you a large resistance change. So here the dynamical range is restricted. Here it's getting weaker, but it's not restricted. There's in that sense no saturation here, which is good, and you do not depend on the exact slope of the transition edge curve. So the transition edge sensor, so really the translation from T to R depends on how steep your curve is, and you have to re-optimize this actually every time again when you restart your run. You need to measure what it is. So this is really something with the TSs, which is a little bit challenging. You don't have this with the MMC, so that is nice. Now, how do you take advantage of this? So basically, an MFC has a few key parts. So first of all, of course, if you want to exploit this, we need to have a paramagnet. So the sensor here is basically a paramagnet. Then you apply a weak magnetic field in order to magnetize it. And then you have on top of it, you have an absorber. And so this, for example, this could be sapphire or silicon. And now if you have a particle here depositing energy, it heats up the absorber. So the whole thing is also operated at millikelvin temperature. We are really, really cold. You have a small energy deposition here. You're heating up the absorber. The absorber heats up the sensor. The sensor now heats up, changes its magnetization. Now you have a little coil here that is picking up the change in magnetization. And in the end, what you are measuring, again, we had this yesterday, you use a squid that is actually observing that change in magnetization. So this is the trick here that we did yesterday already. And also then, yeah, you need to have a thermal bath in order to get your sensor back in the end. So this is basically the key idea is really just to have your particle, the energy deposition, change the magnetization, and you pick this signal up with a squid. So yeah, this is basically the chain of what is going on. Energy deposition causes a temperature rise, causes a change in magnetization, and you can then measure the magnetic flux change in the squid, giving you a voltage signal. And then the pulse that you get looks more or less the same as for a TES, because in the end, yes, please. Sorry, say again. So first of all, we also need the coil to actually get a magnetic field in the first place. And then normally the problem is a little bit that the squid is far away. So this is not necessarily just from the electronics routing. The squid is normally not in the same place as the sensor here, so you need somehow, so the change in magnetic field would actually give you a change in current, which then here's another coil, which would then give you a second magnetic field that's being changed. And so the problem with this being or needing an extra coil here is because the squid is sitting somewhere else than the sensor. So that's the whole reason. So then, yeah, the signal that you're getting is similar to what you get in a TES. So we are again measuring over time, and so you get an increase in temperature, or in the end, really in voltage after the translation with the squid. And the height of it scales in the end with the amount of energy that has been introduced, and then the decay time depends on the heat capacity of the whole system and the strength of the thermal link, so the heat conductivity. Now that is what I just said also to you when you ask how do we know that the film burner works. So the moment on this absorber, when you get here an extra helium film, then you increase the heat capacity here, and so this means the decay time gets longer. So the moment that we see that our pulses have a slower and slower decay time, this suggests that there is actually a heat capacity building up that we don't want. And then on top of it, again, the pulse, the amplitude also itself gets smaller. But then you could ask a question, okay, maybe how can you distinguish between a small energy deposition or a large energy or something where how do you know that the amplification factor is missing? Could be also just a smaller energy deposition, but again, also the pulse shape changes if you have extra helium here and a larger heat capacity. So by the change of the pulse shape, we can actually say, okay, film is accumulating. So then, just as a demonstration of how nicely they work, and I should say that these results here were done with an MMC which was specialized for gamma rays. They are not the MMCs to be used for delight, because you can see that in this case the times they are seconds long, so these are super long pulses. You can basically, this is really a design question. You can play with these two factors and decide how long or short you want it to have within given boundaries. So for delight it will be shorter, but this is just one of the R&D devices of a group at KIT, and with these gamma ray MMC. So when you do a calibration with an iron source. So those of you who have ever worked with iron sources or done a calibration will actually appreciate the fact that you have here not normally people say the K alpha line, so it depends on from where you're getting so which transition, which shell you're having. Here it's not one K alpha line, you actually have two lines and they are separated. So you're seeing here one line is at just so below 5.89 kV. The next one is at a 5.9 kV. They are super close. Normally, resolution is just way too bad to resolve this. Here you can resolve them because the resolution is less than an EV. And then there's also a K beta line. In this analysis, these two have been fit, and the K beta was not fit. It was just checked, okay, if these are fit, does the extrapolation to K beta work? And it worked. So this is basically showing you that also the linearity was working fine. So this is just one proof of concept for these MMCs. And so this is basically really, at that time for these kinds of detectors, world leading result in terms of resolution. So they're really marvel. And that is something that, again, Delight is going to use, but in a special design. So basically, the key idea is that you have a wafer and you don't have just one sensor, but you have many sensors on top of it, because in the end you have your detector, you want to have good coverage. So when you have these atoms, the helium atoms coming out, you want to collect as many as possible. So you want to have your vacuum area really nicely covered with sensors, and you don't get it when you just have these micrometer scale thingy. So you really want to put it on a big wafer. So this is a 3-inch sapphire wafer. And then you can cut the wafer in any geometry that you like. And if you have basically a cylinder that you want to cover on the top and on the bottom, you can make them hexagonal shaped. If you want to have the mantle instrumented, you just make them rectangular. And this is basically the idea that each of these cells here is a large wafer, large area microcalorimeter. So that's the LAMCAL, and the goal will be to achieve also resolution of sub 1 EV. And actually, the KT group is at a point where they can say that this is actually achievable. And then per LAMCAL, when you say, okay, you want to have a trigger threshold at about 4 or 5 sigma above the baseline resolution, then you are ending up at about 5 EV trigger threshold. So that's basically telling you that on a single wafer, you have a threshold of about 5 EV. And this is again putting you back on the scale that we discussed yesterday, and the EV scale of energy deposition. So this is really, the new era of devices since the past couple of years-ish, I would say. Now, the original, so this is the drawing I gave you before. The original or the first phase drawing or geometry for Delight will actually not yet be a high cylinder, but instead giving up on the side instrumentation, make this really shallow. So here you can see that basically this is the superfluid helium, and you have here the top layer and you have the bottom layer. And the goal here is, again, because we want to collect as many phonons as possible, and so you want to have really a high quantum or quasi-particle collection efficiency. And when you just imagine in an extreme world, if you have like a super thin helium layer and you have your energy deposition, and then all your phonons go up and they release the helium atoms and you collect them. The larger you get here, the deeper you get, you have losses in all directions. So to first order, the first goal will be to really have this pancake-shaped detector. And then the cool thing is that in this kind of device, you're actually combining two approaches in terms of analysis. So on one hand, so you have your vacuum MMCs and you have your submerged MMCs. And if you have, say, a deposition here, you will have some energy propagating up, you will have some energy propagating down. Photons, if you have a photon that is being released, that could be collected by any of the MMCs. The phonons, our expectation right now is that only the top MMCs can see them. And then how it would look like, and don't worry yet about the funniness of the shape. You will understand better why they look the way they look in a moment. But the point is, here you can say, just by looking at this plot, you have each MMC gives you something like this, gives you a time series. And then you can see, okay, here apparently there's a huge pulse. So this could be from the phonons. And here, anything that's down here, these are photons. And of course, there are also some photons going up here. But you can see that some have a higher entry, some have a lower entry. So you can basically pinpoint to which of the MMCs the event was closer. So this is, first of all, the time series data that you know from CREST and SuperCMS. But at the same time, since there are these top and then bottom arrays, this is in a way more xenon-like, where you have basically just from the hit pattern, you know that, okay, if an event happened somewhere here on the side of the detector, then you would get a higher energy deposition in the MMCs that are closer to the site. So this is really the combination of SuperCMS and CREST-like analysis and xenon-like analysis. Now, coming to background mitigation. So this is again, and this is the picture of all these processes that can happen. And the important part is also that these are actually happen on different time scales. So not only it's not in the creation, but actually in their propagation. And the other part is also that they differ in the amount. Let me actually go back here. If you have a certain amount of energy deposition, the question is, okay, how much energy goes into this part? How much energy goes into this part? How much energy goes into this part? Or said differently, how much photon signal do you get in the end compared to UV and IR photons? And this is what this plot is showing you. And this is also a lot of information. So let's take this slowly. Let's actually start with this on the right-hand side. So we are considering an event as a nuclear recoil. And I mentioned also that yesterday, and it's also something that Marco, I'm sure he mentioned, that if you have a nuclear recoil, the amount of energy that goes into the phonon signal is larger than the amount that goes into ionization and excitation. And this is what you're showing, what was shown here. So for, say, 1 keV energy deposition, most of the energy goes into phonons, some of the energy goes in UV, and then some of and then triplet that later become UV, and only a little bit in IR photons. And you can see that this depends on the amount of energy that has been deposited. And especially if you get to lower energies, if you don't have enough energy anymore to even get to the first excited state, then you don't get any photon signal. Now, the key point is that this whole partitioning diagram is different for nuclear recoils and electron recoils. If you have a 1 keV energy deposition, and it's an electronic recoil, then it goes almost to same parts to the quasiparticles and to the photons. Whereas here at 1 keV, most of it is going into a nuclear recoil. You have questions? Yeah, this is a lot to take in. Yeah, this is a lot to take in. I know that this is a complex plot.
One thing you mentioned here, you said the minimum amount of energy here is what to get?
So you need a 19 eV to excite in a helium atom.
Quasi-particles, you can go much, much lower.
Yes, exactly. Yeah, exactly. Exactly.
But this is peculiar of the superfluid. Because we learn at the beginning of the week that, for instance, for liquid xenon, I do nuclear recoil and I don't have any any energy that goes into it.
Yeah, so the thing is, for helium, you have a very well-defined dispersion relation. So you really can trace back the energy of the measured phonons to the energy that has been deposited. So that's different to the other noble. So that's also you ask the question, okay, why don't you use just hydrogen? It's even lighter, but you don't get a very well-defined dispersion relation. So that's a key difference, really.
What is the trick? So why it's easier to, sorry for the ignorance.
No,
Why
please.
it's easier to excite phonons in a superfluid?
No, I wouldn't say it's easier to excite phonons. It's the question is how is the phonon information connected to the original information? So you do get phonons also in other liquids.
No, but
There
here,
are long-lived superparticles.
Yeah.
In xenon, when you deposit the heat, it just dissipates
Yeah.
all energies. But here, these protons, they can.
Yeah.
Silicon is very warm, -130. There's no way that you can detect them at -100.
Yeah. And so the other thing is also that the temperature.
tempting is another thing. I'm
Yeah.
just saying, for instance, at the beginning of the week I learned, if I understood correctly, that if let's say I release some energy into xenon, and then I ask myself where this energy goes, there is a very tiny fraction that goes into each.
So what he said is that for electronic recoils, the
Yeah, so like,
for nuclear recoils, it's a larger fraction.
Yeah.
In either cases, we don't see it.
And that's the same here. So for an electronic recoil, less, notably less goes into heat. And that's actually the trick that we use. And that's also for the silicon and germanium and so on detectors. The trick that you use in order to distinguish between an electron recoil and a nuclear recoil is the fact that in an electron recoil, much less heat per deposited energy is being generated. Yes.
You mentioned you mentioned hydrogen as a lighter element that doesn't have it, but there's another element that is one nucleon lighter than helium-4.
Fair enough. But yeah, so first of all, it's much more expensive. And then also, I mean, the nice thing also with helium, so helium-3 at the end, it becomes helium-4. It's really annoying with the neutrons coming in to keep it at helium-3. But then the other thing is also, probably to most extent, I would say it's a money factor because you can actually also do experiments with helium-3. So Quest DMC is using helium-3 in order to try to get there. But then again, so just in an improvement of the mass, so from 4 nucleons to 3 is not that much, and then helium-4 is just much more, much cheaper.
What's nice is you also have this spin.
Yes, yeah. I'm sure Quest DMC will do that part. Right. So then let's translate this actually in something that is more familiar maybe to everyone. So this is typically the band plot that you get. And so you have on the x-axis, you have the quasi-particle energy. On the y-axis, you have the photon energy. And it's the same plot I basically showed you for super CMS. Again, for a given quasi-particle energy, this is where you have nuclear recoils. This is where you have electron recoils. For a given quasi-particle energy, the photon energy is much less for nuclear recoil than for an electron recoil. Or said differently, for a given energy deposition in an electron recoil, much more of the energy goes actually into the photons. Now, one thing is pretty cool in this simulation. So this is an alpha N reaction. What you see here, the neutron, in contrast to a dark matter particle, neutron can multiple scatter. And a scattering, if you multiple scatter, if you let's do it differently. So this is now again. Let me know if I'm losing you, but just let's get to this point. Let's just pick any number. So say we are here at 10 keV. If the 10 keV is deposited at once, then you have a certain fraction that goes in the quasi-particles and UV. If you instead you have a double scatter, so your 10 keV is not deposited once, but let's say twice half of the energy, so you would be lower in so this here, so that would be 1, 0.5 here, your fraction between the two is different. Well, let's go here. It's a little bit more extreme. I'm just sitting here on on an unfortunate part. So here at 1000, so 1 kV, if you deposit 1 kV, most of it, most of it is in quasi-particles, but a fair amount is into photons. If you do 500, the fraction of quasi-particles to photons is much higher. So if you deposit twice 500, your fraction of quasi-particles to photons is different than if you deposit once 1000. So this is really just the same amount of total energy, twice 500 eV or once 1000 eV, but the fraction of quasi-particles to photons is different. And this is now the situation here. The same amount of energy, for example, here in my example doesn't, here for 300 kV, in a single scatter, you get a different amount of photons as compared to in a multiple scatter. And that is actually pretty cool if this can be resolved down to low energies, because if you can distinguish between single scatter and multiple scattering, you can at least get rid of some of the neutrons, because dark matter would never ever do multiple scattering. Of course, life is not always that easy, and you can already see we are talking here about the kV scale. But what we really want to look into is like below 500 EV. And there you see the bands. They don't really separate anymore. So while this is pretty cool, I don't think this can be extrapolated all the way down. But what you still see is that the electron recoil band and the nuclear recoil band is still separated. And this takes a resolution into account. So detector resolution is being accounted for. And this is basically the same idea like for xenon or super CMS IZIP or CREST, the idea that you can separate between those two signals given the different sharing of energy in photon and quasi-particle energy. Now coming to the funny shape of the pulses. Now, this is again the Heron detector, just to really give it the credit it deserves. And this is again proposed in the 80s, built in the 90s. And this is an actual measurement. And now if you have here, they were using back then a source here, a radioactive source. And it generates both photons and quasi-particles. Photons propagate much faster than the phonons. So the photons to reach your sensor, they will be faster than a phonon. So you can basically distinguish between a photon signal and a phonon signal. And so by measuring the full pulse shape, this is now looking a little bit different from what I've shown you before, you can actually measure how much of the signal went into photons and how much signal went into quasi-particles. So this is actually, in terms of analysis, you can already imagine that there's a lot of complication to it, because you don't just have this one nice pulse, but you have many. But at the same time, it makes it also super exciting, because the more features you have, the more information in the end you have to learn about your event. So then, coming to the background source, and this is a slide I'm stealing from Robert Hamann Xenon, because I really like this organization of the background. So we have here, it's liquid xenon. I just wrote now liquid helium on top of it. But the point that he is making is that first of all, the two colors that distinguish between red, which is any kind of nuclear recoil, and blue, any kind of electron recoil, and you have different sources. So the dark matter would do a nuclear recoil, but you have cosmogenic and then solar background, so you have the neutrinos, and the neutrinos could do a nuclear recoil effectively, or a electron recoil. The muons, the biggest problem with the muons is not the muon itself, but the cosmogenic neutrons it generates. Then you have radioactivity, and then you have the internal backgrounds. And one thing that is actually super cool about helium is helium-4 is an ultra pure quantum state. You don't have, at these temperatures that we are operating, all stuff. So first of all, it has no intrinsic long-lived particles. So silicon is annoying, because silicon is silicon-32, which is a beta decay. So your silicon always has an intrinsic background. Helium-4 is helium-4, period. Then at these temperatures, no other species survive. They freeze out, and you basically your volume itself is free of any of the radioactivity. But still, I'm keeping this here for completeness. And then the different strategies to mitigate is, first of all, we discussed going underground, shielding, very pure materials, active fetus analysis. And that is actually, the different parts that will address different parts of your background. So going underground, shielding, active fetus will help you reduce the cosmogenic neutrons. Shielding material selection will help you with shielding against your radiogenic backgrounds, your internal backgrounds, and then if you use analysis, you basically, this is the moment when you can distinguish between your nuclear recoil and the electron recoil, and this is now the part when you also could do a multiple scattering rejection. You could also discriminate against the neutrons. But again, this is something that is super speculative, but also a reason why we strive for multiple scattering rejection, because the neutrons in the end, in addition to accidental backgrounds, are actually the biggest danger in terms of backgrounds. And again, this is a big if. And now bringing this all together, so this is a simulation of the expected background if there's a moderate shielding. So there's a couple of centimeters of polyethylene, for example, and water around. Then, and this is again a lot, there's the energy scale of your backgrounds, this is the rate of backgrounds. VDA stands for Vue des Alpes. This is the underground laboratory where the light will be built. And you see, I just basically want to highlight here, this part here and this part here. These are, so the black is the sum of all, but this here and these here are both electron recoil background. So this is just this entire plot. The take-home message really for you is that after a certain amount of shielding, the dominating background is coming from ER, and that's why it's so interesting to have the two different signals, the phonon and the photon signal, to discriminate between the two on analysis level, because this is dominating right now the expected background level. And then, just if you take this background level into account, so let's just focus here on this parameter space, dark matter mass, 1 GeV, then the light is actually going to probe parameter space in the first iteration to the 100 MeV scale, and this is at a very moderate exposure. So kilogram day means if you have a kilogram of helium, you will need to measure for a day. So in this case, it's 150 gram of helium, so you need to measure 7 days. But basically, in 7 days, you carve into this parameter space. So this is the nice thing, again, that I also mentioned yesterday already. With these, in order to probe the light dark matter parameter space, since there is still so much free space, you don't need huge exposures. You don't need kilogram years or ton scale masses. You can live with the gram scale masses and small exposures. So let me see. So given we had a little bit of discussion. I will just probably show the last 2 slides and then come to a conclusion, because we are at the end, I think. So coming back to this plot. So this is actually the projections that Harold generated, but this is not really Harold projections, because that was just also under the assumption the shielding is shielding from super CMS, and then there's some helium inside, so it was nothing Harold specific. But basically these are the projections for different thresholds and different exposures. And this is maybe just also a plot that I want to show in order to trigger a little bit your skepticism when you see these kinds of projections. So experiments like to do put something out that is super bold, so that everybody's saying, oh, wow, this looks really amazing. This is not going to happen anytime soon again. So we are just so at the scale that we can resolve a single electron volt, and this is not a resolution, this is threshold. So the idea that you get to a detector that is at a size of kilogram years, so it's really getting large, And a threshold is at a milli eV scale. I'm not. I have a lot of imagination, but I'm not seeing this too soon. So you can basically ignore number 4. I've removed that, and already that will be really challenging. I think we have ways to get to this point. So 10 eV threshold, that is in sight. So not in the first iteration of Herald and Delight, but that will be the next generation will get there. So this is really feasible. This not so much, and yeah, this is impossible. So just so when you see these things, be critical, be skeptical. What is just check, okay, what is the state of the art, and then if you see that really, especially resolution and threshold, if this is orders of magnitude better, you can basically ignore those limits for now. Um,
This for nuclear.
this is for nuclear recoil, exactly. Yeah, yeah. Nuclear recoil, 1 milli eV resolution. It's
Can I make it? Probably a lot of people here, including some organizers, will disagree with this. But I mean, one should also keep in mind that a fixed cross section going lighter, let's say the theory motivation, the theory prior goes down exponentially. So I think it's so.
I wouldn't say exponentially.
and one say exponentially.
It's more than for me. It's square.
Uh,
So
Square.
Gaussian. Square is an
Okay,
exponent. So I mean, I think this looks great.
so yeah, I think first of all, I agree. I mean, once you are in this regime, yeah, going really just pushing in this direction first makes sense.
So pushing down is just a matter of just a matter of sorry. I'm confused.
Yeah, not luminosity, but exposure. Yeah, yeah, yes, yeah,
Wrong brain.
yeah, yeah, exposure. Yeah, yeah, yeah. In the end, it's luminosity.
So it's just
Yeah.
a matter of more days.
Yeah.
But backgrounds are the real, right? Like in the end, if you make it bigger, but the backgrounds are.
Yeah, exactly. So there is nothing qualitatively. That's what I was asking. So is there like an obstruction going down that is related to new backgrounds you would encounter, or
New backgrounds. I don't know new backgrounds. I mean, at some point we will also expect to be in an area where we can distinguish between a neutrino signal and a dark matter signal. Backgrounds in yeah, yeah. That's why I'm saying it's a neutrino signal. I'm not yeah, yeah. So then yeah, when the helium reaches here, then actually this is a nice way. So this is boron 8, and this is actually a nice way to start probing the neutrino region. So it just changes the narrative of the experiment, but you're transitioning from one signal region to the next signal region. Yeah. Yes. Yeah, you're going back to Heron. Yeah. 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 This is the solar neutrino region. Yes. Yes. Um, Yeah, so maybe again we used up quite some time at the beginning. I can't really show you uh, the spherical counter anymore. So let me directly skip to the very last slide, because this is also the end of the lecture series for myself. So again, yeah, we have many orders of magnitude to scan, and really the quest for direct dark matter detection. This is really, we are now in a phase where we have these super sensitive devices, and this is actually pretty new. So it's not like we had this discussion yesterday. It's not like we are measuring with that. Yeah, precision sensitivity since 100 years. It's actually just very few decades, and actually at this precision that we can really move away both in terms of cross section really deep and in terms of mass range. This is just yeah, from this century really, and we are just so getting started with really cool experimental approaches to probe it. Then it's not just the classical WIMP searches that direct detection is doing. We are really having this broad range of different WIMP models, or extended WIMP models, light dark matter bosonic models that you can probe. And it's not just really the WIMP hunter. In general, when you take together the WIMP models and the bosonic models, direct detection particle experiment can probe more than 12 orders of magnitude, so we're really going from TeV to the eV scale. And in order to get there, we really need progress on both sides, so experiments and theories. And this is really something, yeah, where we need young creative minds to push further in these directions, because we still have a lot to cover and to probe. And with this, I want to thank you for your attention. Mhm. I know. So these wafers here, so the MMCs, they can easily measure photons. That's not a problem at all. So they are basically originally built. And let's actually get back to here. It doesn't really matter where the position is coming from, whether it's from a photon. Yeah, exactly. So the photons coming in, you heat it up, you measure it. Exactly. So they are actually great. And I should actually also mention, since you're asking how you measure it, what I didn't say that right now, what Delight is trying to see is whether actually the photons themselves can actually be measured also directly in here, because theory predicts it can. And we have a little setup that is testing it. And right now it's looking promising that that can actually also measure it directly, so not just by the evaporation, but that is still to be confirmed. But the photons, they can be really, the photons hit the absorber, they will heat it up and be detected. Yes. Yes. There were more questions. Yes, please.
You showed we are seeing many hydrogen instruments. Can they be used to test standard model physics like physics or?
Yes. So for example, actually the Katrin experiment, which is testing standard model and neutrino physics, they are now working on an upgrade that will use MMCs. So I don't know exactly where and how, but basically, yes, they can also be used for that. Or for example, the ECHO experiment, which is also a neutrino mass measurement using holmium decay, and yeah, to measure the neutrino mass, and they are also using MMC. So yeah, you can use these devices also to probe standard model physics. Yeah. Yeah. Yes.
There is no more question, so you can go.
Just briefly, so in Oxford they told me there was a project to use SNSPDs
Mhm.
for neutrinos. I was just wondering if you know what would be the advantages of using SNSPDs compared to the MMCs, you know, in your view.
Yes.
Any, I don't know.
So just so you know what Laura is talking about, in this case, it's not directly yet the answer to you, but I just want to take everyone with us. So SNSPDs are superconducting nanowire single photon detectors. So they are basically, so yeah, you learned now about, or you knew probably also before already, superconductivity in detail. And so the key idea is here basically the moment you have the absorption of any kind of particle, then your superconductor is heating up a little bit, and it's not a superconductor anymore, but it's either in transition or it's yeah, just normal conducting. And so in this moment you acquire a voltage across it, because again it's not superconducting anymore, but because you have a hotspot from the energy deposition, you can measure a voltage. So that's first of all that idea. I think what is really great about them is that they have super low dark currents. I think this is really a strong thing for them. And then the question is whether you want to use them as sensors or as a dark matter target. In terms of sensors, I think what is yeah, I'm not a sensor person. That's why I can't really say something with, or take my answer with a grain of salt. I think that's what I'm going to say. In terms of the flexibility in the size of your wafer, I think it's hard with them to actually get wafer sized sensors. So I think in a tiny, if you just have small coverages, they are super nice again because of their very low dark currents. But when you want to have significant coverage, I think this is where it's challenging. Yeah, but. Yes, please.
Don't worry, we're not going to get there.
So, but at some point we will, and then we measure the neutrinos. I mean, so in terms of what it tells us about theory, this is actually bringing me back um, to this beam really. This is just really a so this is actually always just one dimensional, which is not entirely fair because there are different models with different couplings and so on and so on. So it's really a multi-dimensional picture. And just because in this little region we hit a barrier, an experimental barrier, doesn't really question the entire idea of dark matter, for example. It's really just keep this always in mind. We are really probing small areas. And in terms of experiment, it's suggested if you can, then we should really measure the neutrinos in that region. In terms of theory, it's so first of all, it's not excluding even that model because it's just so we can't reach it, but it could still be there. So yeah, I think in terms of theory, it doesn't change that that much, to be fair. It will change, I think, what will be really nice if we can probe the different relic targets. So these are actually giving us at least some exclusion of certain production mechanisms. So this will be helpful. Yeah. Or find something. I mean, that would be even more helpful. Yeah. Okay. More questions. Okay.
If there are no more questions,